Hello everyone, welcome to the third lab of the semester where we will be building a series RLC circuit and a parallel RLC circuit, also known as band stop and band pass filters, respectively. I think in this intro part I will be going over why they're called that and what properties that these circuits have, much like I did for last week's lab. So let's go ahead and get started. So I've drawn a series RLC circuit where we have a resistor, a capacitor, and an inductor in series. Much like last week, we will be creating a AC signal using the function generator, and we will be measuring our input signal, and our output signal in this case will be measured over both our capacitor and our inductor. I think I will keep the same color scheme as I did last time, where channel 1 will be the yellow channel in our VN, and channel 2, the blue channel, will be our VOut. And over the course of the lab, we will see how changing the frequency changes our output signal. Like I said previously, the series RLC circuit is also called a band stop filter. And let's just briefly discuss why that is the case. As the name implies, there are a certain range of frequencies, or a bandwidth, for which the output signal goes to zero. So if we have some input signal at some certain frequencies, our output signal is very diminished. If we were to plot the gain of our input signal and output signal versus the frequency, where in this case I'm just having the gain be the ratio of the output and the input signals. Last time we used this logarithmic scale, this 20 log of our gain. But in this lab, we're just going to be using just the plain ratio. Makes it a little bit easier. At low and high frequencies, our gain is going to be close to 1, which means that our output voltage is going to be equal to our input voltage, or the voltage drop over these components is going to be essentially corresponding to the voltage drop over the entire circuit. Let's just briefly discuss why at low and high frequencies we would see most of our voltage drop over these two components. Let's talk about high frequency first. So at high frequencies, the capacitive reactance from the capacitor, or like the impedance of the capacitor, is very small because there's not enough time for charge to build up on the capacitor, which means that the field that it creates that resists the flow, resists the field from the flow of charge, is very small. And so it's almost like it's not there. But for an inductor, the exact opposite is true. So for an inductor, a very fast alternating electric field creates a very strong changing magnetic field inside the coil, which creates a very strong alternating electric field in the opposite direction of current. So the impedance from the coil is very high, and so most of the as our frequency tends to infinite, or like very high, most of the resistance in the circuit is over this inductor, and so when we measure the voltage drop over these two components, it's essentially going to be equal to the voltage drop over the whole circuit, so it's going to be equal to our input signal. So that's high frequency. For low frequency, it's the exact opposite. Low frequency, very slow changing electric field, so the inductor really doesn't have a big role in the total impedance of the circuit. The magnetic field that it creates is almost non-existent, so it really doesn't create a backwards electric field that resists the flow of current. However, the capacitor, with this low frequency signal, has enough time to build up a charge on the capacitor such that it creates an electric field that resists the flow of current. So most of the impedance comes from our capacitor, and so when we measure the voltage drop over these two components for the entire circuit, most of the voltage drop is going to be over this capacitor. So the output is going to be close to equal to our input. Hopefully that wasn't too fast. So that takes care of either end. Low frequency dominated by the capacitor, high frequency dominated by the inductor. But there is a point in between called the resonance frequency, and it's the point where the inductive and capacitive reactance are almost the same. And not only are they almost the same, they're 180 degrees out of phase, so they deconstructively interfere with each other, so it's like there is no voltage drop over these two components, so most of the voltage drop is going to be over this resistor, which means when we measure over the V out over these two components, it's really small. Like the change in voltage is going to be negligible. So this would correspond to a V out close to 0, which would be a minimum for our signal. That means it goes from gain of equal to 1 down to 0 back up to 1. And that's why it's called a band stop filter, because there is a certain range of frequencies where the output voltage that we're measuring over these components is really tiny. And then I think you've also seen that I have this FL and FH. These are our low frequency and high frequency cutoff. If you remember from last lab, we found the cutoff frequency for our low pass and high pass filters, and it corresponded to this half power point, where our V out was equal to the power of our output signal was half the power of our input signal, which means that the voltage of our output signal was 1 over root 2 times our input signal, which if we were to calculate what our gain would be at that point, well, substituting in 1 over root 2 is equal to 0.707. So this is the half power point for our band stop filter. So this is kind of where we've decided that these range of frequencies corresponding to our low cutoff and our high cutoff are the range of frequencies that are being suppressed by our filter. So we'll come back to this a little bit later. We'll need to find these during the experiment so that we can calculate something called the quality factor. Now let's talk about a parallel RLC circuit. Okay, so here is our parallel RLC circuit, and also called the band pass filter, which is sort of the inverse of our band stop filter. So there are a certain range of input frequencies that are not suppressed. They're allowed to pass through unimpeded, and we can kind of see on this plot to the left what it would look like. So here again is the gain versus a range of frequencies, where this is pretty idealized, having a gain of 1. In actuality, it's never going to be 1 because there is always going to be some voltage drop over our resistor. But if we imagine that our resistor is some arbitrarily small value, we can think about how our gain would approach 1 if all the voltage drop was over these two components. But for the purposes of just rough drawing, we can think of a maximum value of our gain being 1, where our output signal is exactly equal to our input signal. When we do the experiment, we're not going to find that. and actually, we're going to be using two different resistors, a 10 ohm and a 100 ohm resistor, so we can really see how the resistance changes the peak of our band pass filter. So anyways, there's going to be some maximum value, and relative to that maximum, whatever that maximum is, we'll have to experimentally find it for this lab. There's going to be, again, some cutoff frequency. So for the idealized case, this maximum is 1, and so our cutoff frequencies for our band pass filter would be 1 over root 2, or 0.707. However, this is going to be something smaller. Let's talk about why high and low frequency signals are suppressed for a parallel RLC circuit. Like we just discussed for the series, for, low frequencies. Well, actually, before we get to that, now that there is a branch in our circuit, the current has a quote-unquote decision that it can make on which path it takes through the circuit. And as often is in physics, the path that is taken is the path of least resistance, this kind of ubiquitous Hamiltonian principle. For low frequency signals, we know that the impedance from the capacitor is really high, but the impedance from the inductor is really small. So it's just going to go down this path where the inductor is at very low frequencies, and so most of the voltage drop is going to be over our resistor over here, so the voltage drop over our inductor is very small, close to zero. Or not just over our inductor, but over both components. Well, it's going to be going through the inductor. So it's going to be really small because it's going to go through this path of, through the inductor. At high frequencies, the exact opposite is true. So the impedance from the inductor is really high. So instead of the current going through this, it's just going to go through the capacitor, which at high frequencies, the impedance of a capacitor is really small. So again, if you measure the voltage drop, because it has this easy avenue for which it can travel, it's going to be close to zero. But there is a point, again, our resonance frequency point, where now there is no optimal path. The resistance or impedance, the inductive reactance or capacitive reactance are roughly equal to each other, so there is no preferred path, which means that there is going to be some maximum voltage drop over these components. And again, this corresponds to when the phase are completely in phase with each other, so they're constructively interfering with each other. Constructively interfering with each other, unlike how in the series RLC circuit they were destructively interfering with each other. Okay, so that resonance point will be the point where most of the resistance or most of the voltage drop is going to be over these components. And I think that about wraps up the kind of discussion about these two circuits. Hopefully it makes sense. Again, this is more of a kind of overview of kind of these general trends. These are the kind of plots that we should be getting whenever we use our data. One final thing that I wanted to discuss is this quality factor. Well, I guess the quality factor and the resonance frequency. If you look in the manual or other resources, you can see how we can derive what the resonance frequency is. But I'll just state it here. It's 1 over 2 pi times the square root of our inductance times our capacitance. And once we measure our components, we will be able to calculate this value, and it'll help us to find our resonance point. Okay, so, and most importantly, this corresponds to where either our maximum or minimum is for our various filters. This other thing that we're going to be measuring for this lab is the quality factor. And the quality factor is just a number that describes how selective our band stop and our band pass filters are. So it is going to be equal to our resonance frequency, whatever that frequency is, over our bandwidth. So the difference in our high cutoff and low cutoff. So if you can imagine, for a very small bandwidth, so like a bandwidth that rejects a very selective amount or passes through a very selective amount of frequencies, the quality factor is going to be really high compared to one where we have a super wide bandwidth, which allows a bunch of frequencies or disallows a bunch of frequencies, depending on whether if it's a band stop or band pass filter. So we're going to be building 4 circuits in this lab, 2 band stop and 2 band passes. And for each of those circuits, we're going to be measuring, we're going to be using 2 different resistors. And we're going to be seeing how these 2 different resistors affect the shape of our filters. These are the components I've chosen for the experiment. Our lab manual asks us to get a 100 nanofarad capacitor, an inductor, a 100 ohm resistor, and a 10 ohm resistor. I'm sure you all have noticed that this capacitor is a bit larger than our other components. And the reason for that is when I was doing the experiment beforehand, before filming, I was running into some issues having the experimental value match up with the theoretical calculation for the cutoff frequency. And I isolated the problem to the capacitors that I was using. They weren't staying at nearly a constant enough value for the entire run of the experiment. So I busted out this big guy. It's a bit of an overkill for the experiment, but it stays at a nice, or nearly constant value. So for the purposes of filming the experiment, it works very well. And I can just add it in. I can attach the wires here and add it into the breadboard like any other component. So I'll be using this for the whole experiment. All right, let's go ahead and measure our components. So let's start with these resistors. So this is what is this? Brown, black, black. I guess it goes this way. Brown, black, black, or 1, 0, 0, 10 times 10 to the 0, also known as 10. So looks like our 10 ohm resistor is actually, okay. Looks like it's sitting there at 10.1 or 10.2. We'll call it 10.1. And here is the 100 ohm. So brown, black, brown. So 10 times 10 to the 1. And this is a 90. We'll call it 99.1 ohms. It's bouncing a lot more than I was expecting. Okay. Well, it's like going back and forth. So the lowest I saw was 89.8, and the highest I saw was like this 99.3. So we'll call it 99.0 as the difference. So 99.0 for our 100 ohm resistor and 10.1 for our 10 ohm resistor. Okay, let's measure our capacitance. So change this. So set to this scale. This is 0.1 microfarads or 100 nanofarads. So what do we have? So this is our capacitance is 102 nanofarads. All right. So those are our measurements. The inductor, we actually can't measure. So we don't have the ability to measure the inductance, but we know roughly what it should be based on the color scheme. The color scheme for, or the color code for inductors is the same as resistors, but the scale is slightly different. So this here is a red, red, black, and silver. So 2 to 0, and the silver is tolerant, so it has a, it's 20. Okay, so it's this value plus or minus 10%. Silver is 10%. And what I mean about the color code, I'll compare it to this resistor. So for this resistor, it's our 100 ohm, so it's brown, black, brown. So that means, so brown 1, 0, 1, so it's 100 ohms. The inductor is similar, except it's scaled down by 10 to the negative 6. So since this is red, red, black, this would be 2, 2, 0. So this inductor is roughly 22 times 10 to the negative 6 henries, or 22 microhenries. Okay, so those are our components. I'm going to go ahead and measure, or not measure, I'm going to calculate our theoretical frequency, our resonance frequency. So that is equal to 1 over 2 pi times the square root of our inductance times our capacitance. So let's go ahead and figure out what that is. So 22e negative 6 for our inductor times what? It was 102 e to the negative 9. Okay, so our resonant frequency should be theoretically at 106 kilohertz, right around there. So we can use this as a reference to find it. Although when it actually comes time to find our frequency, it's fairly easy because just from we can see where the two channels are completely in phase. You'll see when I get there. So let's go ahead and build the circuit and start the experiment. I've constructed the band stop filter on this breadboard, so let me trace through the path that the current will take. So I have power coming in from this red lead, coming into this far left column, where I have the resistor. Right now I have the 10 ohm resistor connected in, so again, everything in this column is connected, so it goes to this resistor over here, and it jumps to this row. Then on this row, you see this green wire. It's going up to the capacitor up here, so it's a little bit off screen, but it's connected to one of the leads of the capacitor, and then the second lead comes down here to this other row where it's in line with this inductor, and this inductor goes straight to ground. Up here is the probe, the yellow probe, which is measuring our Vn, so just the signal that we're getting from our function generator. And this other probe, which is blue, you can't see it down here, but it's measuring, it's in line with the capacitor, and it's measuring over to ground. So here's ground. Oh, and I guess here's ground for the function generator, so this leads back to the function generator. Okay, so that is our series RLC circuit with our 10 ohm resistor in. Let's take a look at the function generator and the oscilloscope. Get this set up. It's pretty good. Okay, so for the function generator, right now I just have it set to 1 kilohertz and 4 volts peak to peak. I'm going to keep it at a 4 volts peak to peak for the entire run of this experiment, so that's always going to be our input. I guess let me briefly talk about the plan for this experiment. So we have two circuits, the band stop and the band pass filters, and then for each of those two we're going to be using a 10 ohm resistor and a 100 ohm resistor. So we're going to need to do 4 sweeps of frequencies for the entire experiment. And then we will be finding the quality factor for each of those 4 circuits. My idea is that we find the resonance frequency first, have it be our first, data point, and then go through and, do our regular sweep, and then afterwards find the low and high cutoff frequencies. So if we look at the procedure in the experiment, we are asked to find the gain for these various frequencies, and we're not converting it to this decibel scale. It's just going to be the output over the input. And we need to make these plots of our gain versus our frequencies, much like we did in the previous experiment. Okay, so one thing that I want to, before we start, I want to make note of is down in like step 7, so I'm jumping a little bit ahead, is we are going to plot, okay, it says, using the table, plot the gain versus frequency curve for each resistor. Plot both curves together on the same graph so the difference is clear. Again, do not convert to the decibel scale. And then pro tip, it does, however, help to plot frequencies on a log scale. And I'm going to kind of be running with that. So having gone through the experiment, it does help to plot our frequencies on a logarithmic scale. And the frequencies that we're going to be measuring over are from, our lab manual asks to measure from 1 kilohertz to 1 megahertz. So that's 3 orders of magnitude if we start from 1 kilohertz and go all the way up to 1 megahertz. So I will be kind of strategically measuring different frequencies at different scales so that we can get a nice plot, or so that we can all get a nice plot from our data. So that's the plan. Let's find the resonant frequency for this first band stop filter and see if we can get started. Okay. On the display, hit the measure, I have the peak-to-peak voltage of channel 2, this is our V out, on top, and the peak-to-peak voltage for our channel 1 on bottom. So very top is our blue out, the very top is our output, our channel 2, our blue channel, all the same thing, and channel 1, our VN, is on the bottom. And I did this just because when I was calculating the gain, it just helps to have the two numbers, actually represent like what's in the numerator and what's in the denominator. At least for me, it helped for me. Okay. I think I would like to run through an entire sweep of frequencies just to show that what we see on the oscilloscope does match what we talked about in the introduction. So right now, at low frequencies, they are the same. They look nearly the same. But for this band stop filter, we should see that the output channel should get smaller than our input channel until it reaches like some minimum, and then it should start to raise up again until they are roughly the same. So I just wanted to show that behavior, and I'm going to run through a whole bunch of the frequencies just to see that. I may have to re-auto things because when the relative channel gets, the relative displays of both channels gets slightly off, you'll see, it kind of gets a little wonky, but let's run through it. So right now I'm at 1K, so let's go up to like 10K, and even now it's going to get very spread out. So it looks nearly identical still. Maybe the blue is just now starting to shift and get out of phase. So let's go in steps of 10K and see what happens. So the overall peak-to-peak voltage is going down. And we can start to see that the channel 2 is getting smaller. So right now they're still at the same scale. It's 200 millivolts peak to peak, but we're starting to see that our output channel is reaching this minimum, and I may have to re-auto it so it stops scrolling, or I can just stop. So it's around 90 kilohertz. And remember, from our calculations, our resonance frequency, this minimum value, should be at around 106 kilohertz. So we're getting there. We're getting pretty close. So let's go at 100. Again, a little. So we are close to the minimum. I just increased the scale of channel 2. I'm actually going to re-auto it just because, so we get this. It stops the scrolling. Okay, and then if I increase by another 10K, we can see that it actually has passed that minimum, and now it's starting to go back up. So we can see really here, right in this range, that we do have our resonance point, and you can see that they're exactly in phase. So we've reached the bottom minimum of our band stop filter. Let's keep going to see how eventually the V in and V out start to return to their original waveform. So they're now at the same scale. Let's actually decrease them both. And we're in the 300 kilohertz, so that's pretty high frequencies. And we can just start to see that as we start going up to a megahertz, the our two waveforms are nearly in phase again. So their peak-to-peak voltages are on the same order. Not on the same order, they're on like the same scale. They're roughly equal. So we saw this, this definite, our gain was roughly 1 as at the start, reached some minimum value at our resonance frequency, and then now it's back up, our gain is back up to 1, or close to it. So let's actually go back and find that resonance frequency. So it was around 110 by the looks of it. Re-autoed it, measured it. So the easiest way that I find to find these resonance points is scaling up the two waveforms so that they're exactly the same size. So even though that, this is the scale of our channel 2 is only 50 millivolts, and for our channel 1 it's 200, so the channel 2 is being scaled up a lot, so it looks the same size as our channel 1, but knowing that at our resonance point is exactly when these two waveforms are in phase, if they're the same size, it's kind of easy to visually see that point. So let's see if I can even find this. Okay, so let me increase it ever so slightly. Down. Increase this one too. Actually, you can see this. Okay, so I'm at 107. So it does look like at 106 it looks slightly shifted to the right. At 108 it's slightly shifted to the left. So at 107 it does look like that is our resonance frequency. Okay. And then just looking at our, if we can make this our measurement. So let me scale these so they're fully inside. So if we were to measure our gain at our resonance point, well, first off, I think I'm saying that our resonance point is at 107 kilohertz. I think we'll say that. And then let's see what our gain actually is. Okay. So our V out is 228.4 and our V in is 881.2 millivolts. Okay, so that's our point. That's our resonance point, and that could be our first frequency. So I think what I'm going to do, now that we kind of found it, I will go back down to 1 kilohertz, and then we can run through our frequencies and kind of choose points that are to get a nice collection of values around this 107 resonance point and get a nice plot. So let me do that. Okay. So let's go back down to 1 kilohertz. So at this point, I would recommend that you pull out an Excel spreadsheet or have one open, because I think it'll be easier for data collection in the long run. We wanted to get a nice plot from our data, so just going ahead and having a column for frequency for our V in, our V out, and then you can very easily calculate the gain by using Excel's functions, I think would be advisable. So with that in mind, let's start taking our values, or measuring our values. And I think I will kind of strategically choose the points at which to measure so that we can get a good logarithmic plot. Okay, so down here at 1 kilohertz, we have our V out is kind of bouncing back between, actually, well, okay, so, let's see if we can get it to stop. All right, we'll call it 4.08 and 4.04. So our V out is 4.48, our V in 4.4 or 4.04 volts. This is at 1K. So that'll be our first point. Let's jump up to 2500. Okay. V in or V out of 4.03 and V in of 4.0, no, between 4.01 and 4.04, so 4.02, 4.03, around there. All right, so that was 2.5K. Let's jump up by another 2.5. So at 5K, our output is 3.94 and our input is 3.96. All right, 3.94, 3.96 at 5K. Let's go up by 5,000 again. So at 10K, what do we have? At 10K, our output is 3.72 and our input, our channel 1, is 3.73 volts, and this is at 10K. Okay, so that kind of gave us a, I guess 4 points for that first 1K to 10K range. So, and I took pretty large steps in there because you can see that it's staying roughly the same. So Let's go for 10K to 100K. We'll go in steps of 10K and just kind of keep it at that constant kind of linear step. So let's go to 20K. 20K, what do we have? 3.12. Let me adjust the scale just a bit. 3.12 and 3.12 for both input and well, that's fine. I guess you can split the difference and call our channel 1 3.14 if you want. So output 3.12, input 3.14 for 20K. Let's go to 30. Output 2.46, input 2.4 or 2.58 at 30. Let's readjust our scale so we get accurate measurements. So at 40K, we have what? At 40K, we have an output of 1.88 or 1.89, one of the two, and an input of 2.07. Yeah, 2.07. Okay. So that's 40K, 50K. V out of 1.48 and an input of VN of 1.68 at 50K. Cool. Let's go to 60. Increase our scale a little bit. All right. At 60, we have a V out of 1.14. Yeah, I'll call it 1.14 or 1.13. Yeah, 1.14 because it's in between those two. All right, and then a VN of 1.41 if we split the difference. And that was at 60K. Cool. All right, let's go 70. Adjust our scales. Okay. So at 70, we have 840. Okay. So between. See if I can stop it there. All right, we'll do that one because it's kind of in between. So an output of 846.3 millivolts and 1.16 volts. Okay. Let's go to 80. All right, that's fine. So output at 80K would be 617.7 millivolts, or 0.6177, and an input voltage of what, 0.9996, I think is what I saw previously. Yeah, all right, or 1.01. I mean, I guess that's, you could put in a volt or 1 volt since it's kind of going back in between those two. Okay, so for 80K. For 90, increase our scale again. Do this. That's fine. All right. So for 90K, our output is what? Lowest is 397, 395. Okay, that's fine. That's good. So our output is 4.403 volts, and our input is 0.9302 volts. Okay. So that was, what did I say for our input? I was focused on the output, so I'll still stick with the 0.403 volts for the output, but I think for the input, it looks like it's bouncing around between this 918 and 924. So, okay. Or 930. Yeah, I guess the 924 is the middle point. So we'll say the input for 90K is 0.9241. If that's not what I already said. Okay, let's go to 100. 100. So for 100, actually I wonder. Okay. For 100, we have 255.5. So I guess that 257 one is the one in the middle. All right, we'll do that. So an output voltage of 0.2571 and an input voltage of 0.879 volts. That's fine. And that's at 100K. Okay, so that kind of got us through 10K to 100K. So our frequency, our resonant frequency, was at 107. So I think in this range, I'll go in steps of like 2K or 2000 hertz. So we'll go from like 101 to 115 in steps of 2000 to kind of give a nice range of points around our minimum. So that's that plan. So at 101, we have 244 point, oh man. All right, I'll do the 249. So 0.2493 for our output voltage, and for our input voltage, yeah, that 0.879 looks to be kind of in the middle. So that can be our input voltage, and this is at 101 hertz. Let's go to 103. Oh, 103. All right. So an output voltage of uh, 0.2336 volts and an input voltage of 0.8736 as our input voltage. That's for 103K. Let's go to 105. Sure. A V out of, let's go with that, 125.8. Yeah, that looks to be, or 0.2258 for our output voltage, and for our input, we can do that 0.8736 for our input. And this is at 105K. Okay, at our resonance, we already made this measurement, but I guess we can make it again. Hopefully it's the same. I don't have it written down yet. We are getting around 0.2244 or 0.220. So we'll call it 0.2244 and an input voltage of 0.8736 around there for 107. You can either use this one or this measurement or the original measurement. Hopefully they're under the same. Okay, so that was our resonance. Let's go to 109. So 109, we have 0.2258 and an input of 0.86. I guess, yeah, we'll use that 0.8736 for our input voltage for 109. Let's go to 111. We have 0.2331 volts and an input voltage of 0.8736. Yeah, that's fine. And this is at 111 kilohertz. Let's go to 113. Let's actually decrease this a little bit. So 0.2455 output voltage. Yeah, 0.2455. It's kind of in between those values. And 0.8. Let's go with the 736 again for the input voltage. And last one for our kind of points around our minimum is this 115. So for 115, we have an we have an output voltage of 0.2609. Is that right? Yeah, 0.2609, and an input voltage of 0.7 or 0.8790 is fine. Okay. Great. Now we can start going in larger steps for the back part of our plot. So let's jump up to, I don't know, 130. Gonna have to scale this down. So at 130, we are seeing 0.4344 millivolts, 0.4344 millivolts for our output, and 0.938 for our input. At 130, let's go to jump up to like 150. Sure. Okay, so 150, we have an output voltage of 0.673, I guess so. Yeah, we'll go with the 0.6734, I think it was, for our output, and 1.07 for our input at 150. Let's jump up to like 175. Really start to see how our input and output voltages are really starting to climb back up. All right. Boop. That's fine. Output of 0.9734, I guess is the one in between. 0.9734 volts output and 1.26 for our input for 175. Okay, let's go up to 200. Scale it down. Okay, 1.22 input, 1.4, or sure, 1.5 output. I'm sorry, 1.22 output, 1.5 input for 200. Okay. Let's go up another 50. Scale down. Increase that. Cool. So output voltage of 1.62 and an input voltage of 1.6 or 1.85. I guess it's 1.63 for our output because it's in between those two, and 1.8. 4.85? Yeah, 1.85. 1.63 and 1.85 at 250. Okay, let's go to like 300. Another 50. Decrease. Decrease. 1.96 output voltage, 2.16 input voltage at 300K. Cool. Let's go in steps of 100,000. So let's go up to 400. So 2.45, 2.44, either of those. For our output, 2.61. Yeah, 2.6, 2.61. For our input, and this is at 400K. Let's go bigger steps, like 150. Okay. Cool. 550, yeah, sure. So output voltage at 550 would be 2.9, sure, and an input of 3.05 at 550 hertz. Let's go another 200,000 up to 750. Okay. Output voltage of 3.2. Yeah, 3.2, and then once I said it, it's going to change. So 3.21, and an input of, actually, but it goes down to 18. Okay, so I guess it is 3.2 because it's going between 0.18 and 0.22. And then input voltage of 3.37, I guess. Okay, and we'll have this be our last point, up to 1 meg. So this is what? 3.54 input? I'm sorry. 3.54 output and 3.5, it's bouncing between, sure, 3.58 input. So 3.54, 3.58 at 1 meg. Okay. So that is our first range of frequencies. I think there's like around 30 points. I think for the next part, when we change up from our 10 ohm resistor to a 100 ohm resistor, I don't think I'll comment on it. I'll probably just I'll use the same frequencies, you know, starting at 1, going up to 1 mega, those same ones that I just went through now, and I don't think I'll comment through it. I'll just kind of have them on display, and I'll let you take them themselves. Okay, everyone. So I'm taking a break from just the data to kind of show you how you can present it in a plot. Like I was saying earlier, I put everything into an Excel spreadsheet. These are the same frequencies that we just recorded in the video, but these are different values. These are from when I was doing like a dry run of the experiment before filming. So These aren't the same values that we just measured, although I guess they should be close. But please use the values that we just did. I'm just doing it because I already have these saved. But I wanted to just show you how you can very easily get a logarithmic plot in case you were not aware. And I just calculated the gain by dividing column C by column B, because it's V out over Vn. So if we go over here and we just kind of highlight our data, insert, scatter plot, well, we actually have everything. But if we move this so that we're just having our frequency versus our gain, we get this linear plot. So it's very squished towards one edge, but if we, let's see, double click on our axis, double left click, it'll bring up this menu. And down here, we can change it to a logarithmic scale. Change our minimum value to 1,000. And so now we have a very nice plot. And you can, I don't know, you can make it as pretty as you want. The one thing that I like is the tick marks. So you can actually see down here the logarithmic tick marks. Okay, so this is how I would like our two plots, and of course once we have, I'm only displaying the one, but you can plot both of them. The gain at 100 and 10 on the same plot. But I just want to do a very brief tutorial on how to get a logarithmic plot in Excel. So hope this is helpful. The other benefit too, before I switch over, is the next thing that we need to find is the cutoff frequency for our high and low values. So we can calculate the quality factor because we need that bandwidth. And the one nice thing about having it all plotted up and seeing what the gain is we can find where exactly our cutoff frequency should be. So again, for the band stop filter, it's 1 over root 2 our max value, and then our max value is going to be 1. It's when our input and our output are equal to each other. So 1 over root 2 is around 7, or is 0.707. So when we go to find the cutoff frequencies, well, we know it should be around between 70,000 and 80,000 for the low, and then for the high, it should be between 170,000 and 175,000 and 200,000. So we'll switch back over to the oscilloscope and find those cutoff frequencies so you can, and again, these are not the same data points that we just recorded. These are ones I did previously, but they're similar components, so they should be around the same value. It should be around 7. You can even see here that my, right there, that this was my, I had the same resonance frequency. Okay, so let's go do that now. Okay, let's find those cutoff frequencies so we can find our quality factor. So, I have my computer right next to me, so, and sorry about I don't have screen capture software on my laptop, so I'm just, very rough. I'm just filming my screen, so sorry for poor, low production quality, but maybe I'm not sorry. You kind of get what you get. I think it was visible. I mean, there's maybe like a little bit of screen tearing, or you can see individual pixels and whatnot, but it's okay. What am I doing? We are at a megahertz. We need to go down to like a kilohertz. Cool. Nice. So this is the point where we need our calculator. So we are around we know that our low cutoff frequency should be around set between 70 and 80. So we'll kind of scan through some points to see if we can kind of find where our gain is equal to this, 1 over root 2. So right now I'm at 70,000. I am messing with the scale so we can get a good recording. That's probably fine. So actually it's going to be between 70 and 60. I read my data wrong, so let's go down to 60. No, I'm blind. It's 70 and 80 because it's decreasing. Yeah. All right, so let's try like 75 and see if we can find this quality factor. Sorry, we'll scatterbrained. So what is our V out? It is 1.175, 0.1715. Wow. 2. Yeah, I guess we'll do that one. And our input is this 1.07. So that's 0.668, which is a little bit far from our cutoff frequency. So again, we're after this 0.707. Let me increase it slightly. Actually decrease it, like 72 maybe. So that's let's go with that 0.7824 as our output over our 1.12, 1.11. Yeah, I'll do 1.12. 0.6985, that's pretty close. It might even be, it's probably this one then. It's probably like 71. Okay, let's try that. 0.816 over 1.12. Supposed to be a point. Okay. So that's a bit high. So what does that mean? It means that I think our 72 is probably our closest. And again, it is kind of doing this range. So I mean, if we did this 7 or 0.724 over this 1.11, I mean, that's even closer. So, okay, we'll call it 72 as our cutoff frequency for our low. Let's go find our high, which is actually between 150 and 175 from my other data. I think I said it wrong earlier. I think I said 150 and 200, but it should be, whoops. And I guess a good indicator is that we're now back kind of at the same scale as that we were just using when we were down at 70,000, so that's pretty nice affirmation. So it's going to be closer to the 70, so let's try like 168. I don't know. So 0.8848 over 1.20. That's already, you can tell it's going to be too big. It's too big, so let's go down. 0.8736 over 1.19, I guess that's kind of in between. Barely anything. All right, cool. That's part of it, man. we 0.834, 8, let's go with that, 0.8228, and this 1.16. That's getting close. It's getting close. Let's go with 160. 0.8064 and 1.14. Ooh, that's pretty good. All right, we'll call it that one. So our high cutoff frequency is 160. Seems around there. So this was a long part, but I think the other ones will go a bit faster. Like I was saying previously, I don't think I'm going to call out the names or like the numbers for this next part. I'm just going to display it, and then when it comes time to find the quality factor, because I don't know what it is, I need to, I'll need to calculate it in front of you all in real time. So, okay, so let's switch out this 10 ohm resistor for the 100 ohm resistor and run through the values again. Okay, so I've switched out the 10 ohm resistor for the 100 ohm resistor. Other than that, the circuit has not changed, so I haven't shown it. Let's go back down to 1 kilohertz. We set up our measuring, and so we can do this. And okay, so we can start our measurements starting from 1 kilohertz and using the same frequencies that we did last time. So let's go ahead and get started. So these, and just I guess one final reminder, the top one, channel 2, is our V out, and the second one is our V in. So here are the values for 1K. Okay. Go to 2.5. Okay. Let's go to 5K. Let's go to 10. $20. Okay, that's for 20K. Let's go to 30. That's 30, 40. That's 40. Let's go to 50. That's 50. go 60. Okay. Go 70. Let's go to 80. $90. $100. Okay, we've actually reached the smallest division of our channel 2, so we can't zoom in any more. So okay, this is at 100,000. We'll start going into our steps of 2K and find our resonant frequency. Here's 101. There's 103. Keep it there. Go to 105. I'm actually gonna see if this 107 is still our resonance frequency, as it was for the other one. Let me increase this, and I'm just looking to see if this is lining up, like the phases are lining up. But it does. It looks like a complete overlap. So it's such a small change. I think 107 is still our resonant frequency. I mean, yeah. All right. So we'll still go with that as our resonance point. Or if not, let me rescale everything. Okay, so make your measurement for 107K. Try to find a good point. Let's go to 109. Let's go to 111. $113. And $115. Okay. So this gets our point around the resonance point. What's our next one? 130. Oops. Rescale everything. That goes down. This goes up. Go ahead and do this now too. Okay. So that's 130. Then we will go to 150. Scale this down again. Okay, 150. 175. It's 175. Let's do 200. Got 250. Okay. 250. Go to 300. Let's go 400. Oops. So we'll do this. There's 300. I'm sorry, that was 400. 400. Let's jump to 550. Hope I didn't mess any of these up. I think I'm good. Whichever. We'll go with this scale. So this is 550. Then we have two more. 550. Go to 750. Scale down. Actually, I'll scale this one down too. Cool. There's 750K. And last one, going up to a meg. Okay, so that's it for the data collection for the plot. One thing that you might have noticed is that we haven't really reached our point where our VN, where our gain is equal to 0, so our VN is equal to our V out. And I think you'll be reflected in your plot. So if we really wanted to get a full sweep for this 100 ohm resistor, we'd have to go much higher. We'd probably get into like I don't know. Actually, we can check. You don't have to record these. I'm just kind of curious. Oops. About when. So I'm in 300. Even then, it's getting close. And then, yeah. So I guess around 5 megahertz is really when we do see a gain of 1. But we don't have to worry about that. Okay, let's go find our cutoff frequencies to calculate our quality factor. So we need to find the low frequency cutoff and high frequency cutoff. Looking at the data, if you've already plotted it out, or if you took the time to plot it out, you should see that the low cutoff frequency is between 10,000 and 20,000 hertz, so much at a much lower frequency than for the 100 for the 10 ohm resistor. So okay, so between 10 and 20, let's go for 15. Split the difference and see what we get. Okay, so 2.25 divided by 316 is that. So It's close. Let's go to 16 and see what we get. So that's 2.15 divided by 3.14. Actually, a pretty big drop. So it's between 15 and 16. Let's, I guess, cut it in half. Go to 15.5. 2.2. Whoops. 2.2. Sure, 2.2. And 316. Well, I can't see it underneath the, behind the camera. 0.96. Okay. Get even closer. So that's 2.24 and 316. Nope, that's pretty close. All right. So we'll say that our low cutoff frequency, this will focus, is at 15.2 kilohertz. Okay. And then for our high cutoff, it's going to be between, looking at the data, between 750 and 1 or kilohertz and 100 kilohertz. So opposite end. Let's get up there. So 750. All right, let's scale this. Let's go like 10K above. So let's see what 760 is. Wow. Why is that? It's kind of like bouncing around. All right, so 216 and 2.16 divided by 3.11. 0.69, pretty close. Let's go to 770. Divided by 312. Okay, so I would say that it is between 760 and 770. Let's go to 765. So 2.18 divided by 311. Yeah, it's close. 0.700 or 0.701. I mean, we can go like 2 lower and see if we get any closer. That's pretty close, though. Yeah, I just plugged in the exact same number. Well, 2. I guess it's like 217, maybe. Yeah. It's like 261. I don't know. 2.17 divided by 3.11. All right. Well, I guess the variance in like the data or like the recordings on the measurements is close enough that anything around this range is going to get me close. So I don't know. Let's try this number again. 760. So 2 point. Let's decrease it. 2.2. 2 divided by 3.12. Alright, well, whoops, sorry, bumped the camera. Well, that one's pretty close. So, it's around this range. We'll call it 760, which I believe was the first one I recorded anyway. So what was my original value that I was getting? Oh, it was... $316 divided by that. Okay, well, that's fine. So 760. So again, much higher bandwidth compared to the 10 ohm resistor. So we'll see how that affects the quality factor. All right, we'll move on to the next part where we will have the parallel RC circuit and go through the same process measuring the band pass filters. I've built the band pass filter, so I now have the capacitor and inductor in parallel. So let me just trace through the circuit real quick. So here is our 10 ohm resistor coming into this row over here, and both the inductor and the capacitor are on this row. So this green wire goes up to our capacitor, goes back down to ground. Our inductor is right next to it, goes to ground. And that's it. Here, the channel 2, our V out, is still measuring over both of them. So you can, it's upstream of our inductor and capacitor, and it's connected to ground, and our channel 1 input hasn't changed at all. All right, so let's, with that, run through the measurements. Like I did with the band stop filter, I kind of want to just go through the range of frequencies to give like the overall trend that we see for this filter. So I have it set to 1 kilohertz down here, and you can see right off the bat that these are at the same scale, but our output, our blue channel, is much smaller. It's never going to get to exactly 0, but we should see a definite peak as we go through the range of frequencies. So let's check it out. Okay, so let's go 10,000, and so even now you can start to see that our so right there we can see how our channel is maximized and they're completely in phase. And then as we continue on to much larger frequencies into like the megahertz range, our channel 2 kind of falls off. Okay, so let's actually pinpoint where the resonance point is, so we can keep track of it when we go through our range of data points. So it should be around 107 like we did like it was for the other filter. So I'm at 102. Okay, it's actually very slight. Let's see. Okay. So let's go down again. So that's 100, 105. 105 looks like it's actually the point where it's most in phase. They look like they're completely overlapping at that point. Although I think at 107 is truly the, let's see, 104. So I'm just looking at the output. So this is 2.03, 2.04, and for our output voltage, and 2.42 at 105. Now this is 2 point. So this is actually a higher output voltage. So this would be a higher maximum. I think just slightly, ever so slightly. Like this is the difference of a volt. So I think I'll call 107 our yeah. I think I'll call 107 our resonance frequency again, which is, again, convenient. It should be the same, or around the same. So 107. All right. We'll keep that in mind whenever we get here. That just means that when we go through all those frequencies, we will stick to the same pattern, use the same ones. And let's go ahead and start. I will, again, not call out the frequencies this time. I'll just have them displayed. Or I won't call it the voltages. I'll let you all decide which ones. I'll just keep it in scale and visible. So let me increase that. 1K. Okay, let's start. Get scaled. Again, this is for our 10 ohm resistor. So for 1 kilohertz, we have our V out of about 188.3, 190. Again, I'll let you use your discretion on what values to use. I think you've kind of seen my, how I usually pick one that's kind of in the middle if it keeps bouncing back and forth. So for 1K, our output, our input, and let's move on. So let's go to 2.5. 2.5. Okay, let's go to 5,000. Okay. Let's go to 10. Let's actually scale this down. Okay, so this will be for 10,000. 20,000. Okay. 30,000. Oops, sorry. Okay, this is 30,000. 40. It's 40,000. Let's go to 50,000. Okay. It's 50,000. 60. Okay, that's 60. Let's see, 70. What do we have for 70? Okay, that's 70,000. 80. Our value for 80,000. Oops, wrong way. Let's go to 90. It's from 90,000. Okay. 100. Cool. 100. I'll go on my steps of 2K, starting with 101. So this is 101. 103. 105. 107. This should be our resonance. So I guess looking at it, our output is our output is 2.05 volts and our input is 2.44, around there. Okay. Let's go to 109. We're getting around the same value. 111. Okay. 113. And 150. Okay, so we have some points around our maximum. Let's jump up to 130. So there is 130. And let's look at 150. Scale it. All right. 150. Okay. Let's go to 200,000. Oops. Do that. And then that. So all right. 200,000. Okay. Let's go to 250. Wait, I'm sorry. Did I skip 175? Let me go back. Sorry if I did it slightly out of order. I think I did. We've usually taken this data point, my bad. Okay, so let's do 175. I think I just skipped it. But in the past we've recorded 175. Okay, so that's 175. Again, sorry about that. And then now we do 200,000. And then we'll go to 250. There's a lot of data collection in this particular experiment. All right, so that's 250. Okay, let's go to 300,000. Is that up? Okay. Let's go to 400,000. Okay, that's pretty good. So 400,000. We have those values definitely starting to get down to our starting values. Let's go to 550. That's what I did last time. Okay, we've reached our maximum zoom for our channel 2. So this is for 550. And let's do 750. And finally, 1 mega. Okay. It actually rose, which is interesting. I saw this minimum around. I'm not sure. All right. So that's our data for our first band pass filter for our 10 ohm resistor. Now let's find the cutoff frequency, or high and low cutoff frequency. So we're going to be finding the point relative to our maximum point. So whatever that gain value is, it's going to be 1 over the root 2, that value, 1 over root 2, relative to that maximum. And so we'll find those high and low cutoff frequencies, and so we can calculate our band pass, so we can calculate our bandwidth, so we can calculate the Q factor. Okay, so I've gone back to the maximum value of resonance. So here we have a output voltage of 2.05 and an input of 2.44, which is 0.840. And if we were to take that number divided by, so that is our maximum gain for this frequency. So it's a little under 1. Ideally, I think it would have been 1, but it's a little less. And if we were to find our low and high, cutoff frequency would correspond to the gain value of 0.59. And looking at the data, that should be a low value of around 5,000 or 50,000 and 60,000. So let's take a look, see if we can find it. So again, we're looking for a gain value of 0.594 or around there. So, I mean, when you recorded it, if you found that it was something slightly different, but it should be around this number. So, so I said between 55 and 60. Let's increase our scale. Okay. So let's see what this is. This is 0.664 over 1.1. And I mean, that's getting pretty close. That's at 65 or at 55 we have 0.64, so that's a difference of a tenth. I'm sorry, 100th. Let's go like up by 1. See what happens. So 0.6. We'll call it 0.68. Sure. Divided by 1.11. Okay, so it's a little bit too high. Let's go 1 lower. 0.644, I guess, was in between, divided by 1.08. Yeah, 0.9. I just saw it flip. That's really close, I think. 0.594. So oops. Yes. So that's within 3 thousandths or close to 3 thousandths. All right. Sure. We can call it 54. 54, 55 hertz. I think that's close enough. So that's our low cutoff frequency. looking at our data, if we are, for our high, it should be between, see, 0.594 should be between 200,000 and 250,000. So let's go to 210 and see what's up. Okay, they're both in scale, which is a good sign, or around the same scale. Again, we're looking for 0.5941 as our, or around there. So this one is, I don't know, we'll call it 590. It's between 596 and 608. So let's just call it like 0.6. Yeah, I think I saw it there too. All right, so 0.6 over what? 0.954. That is too high, so we need to a little bit lower, or go a bit higher, I think. Sorry. So let's go to 220. So that's 0.552, 548, sure, divided by 0.9, between 918 and 924 is what I saw. Even 4, okay, it's fine. We'll do the 924 then. 552. And that is 0.597, which again is pretty close. So our target value was 0.9 or 594. I mean, we can. I did go in a step of like 10,000, so I can go like a little bit. But I think just the variance, that's probably about as close as we're going to get. The way that it's jumping around. So what is that? 558 again divided by 0.918. Yeah, we're getting off. All right, it's fine. We'll do. Shoot, I'll do 2 above too, just for consistencies. 0.542 divided by 0.915. 592. Okay, well that's pretty close. That's as close as we're going to get, I think. So 0.592. So our high frequency is 222,000, and our low was the other one. I actually can't remember it right now. Okay, great. So that's the first low pass. I'm sorry. That's the first band pass filter. Now I'm going to replace the 10 ohm resistor with the 100 ohm resistor and repeat the experiment. Okay, so I've gone ahead and switched out the 10 ohm with the 100 ohm resistor. I'm back at 1 kilohertz. I've scaled it up. And let's do our last round of measurements. So this is at 1K. These are our values. Let's go to 2.5. Yeah, sure. 2.5. Around the same. Not much has changed. Let's go to 5,000. Again, around the same. Nothing's changed. Let's go to 10. Okay. And 20. Okay, definitely an increase in our V out. 30,000. V out of around 145. Okay. Our V in staying constant though, which is kind of interesting. 40,000. V out getting larger. Okay, that's for 40,000. Let's go to 50. Very nice. So this is for 50. Let's go to 60. Scale down. 60. Let's go to 70. Scale down. Increase. Okay, that's 70,000. I'm sure by this point you're tired of taking data as well, but we're almost there. 60,000. Okay, let's go to 70. There's 70. Okay. Let's go to 80. $80,000. Let's go to 90. There's 90,000. Okay, 90. Let's go to 100. Scale down. So here we are, 90, or 100, excuse me. Cool. Now let's do our small increments around our max. So this is 101. Okay. This is 103. This is 105. Oops, sorry. .2 and 3.08, so 1.19 and 311 as our max. Actually, what's it for this? So we are seeing our maximum V out at 1.2 and 3.9. I think that is going to be our max. It's slightly off, so this definitely seems like it's more in phase. Just looking at the two waveforms. So, but looking at our readouts, so that's 1.19 and 309. So compare that with 107, and we have 1.21, 1.21, and 3.9. So it's like ever so slightly larger, I think, on this 107, even though it's slightly out of phase. So I think we'll still go with the higher value as our true max. Okay. So that's 107 and 105. I kind of flipped back between the two. Let's go to 109. Okay. 111. $113. And 115. Very good. Those are the points around our max. So let's go to 130. Okay, 130. Let's hopefully not mess this up again. So 150. So there is 150. Let's go to 175. Oops, wrong one. Okay, there's 175. All right. Let's go to 200,000. Scale this down. Sorry. All right, 200,000. So that's that value. Let's go to 250. Okay, there's 250. I'm actually going to increase 250. Let's go to 300,000. I'm at my limit for how far I can zoom in on the blue channel. So there's 300. Let's go to 400. Okay. There's 400. Let's go to 550. Excuse me. 550. And then 750. Ooh, it's getting a little... Here, I'm going to stop it. Alright, so we can use that value. And then finally 1 meg. And there we go. That'll be our last data point. Great. So that's it for that data collection. Let's find our last 2 cutoff frequencies and calculate our last Q factor. Okay, I'm going back to our maximum, which I believe was around 107. That's what I said. Okay, so that does look like it's 1.2, 1.21, and 310. I'm just gonna double check. Yeah. Yeah, all right. Go with this 107. So I think it's all going to be around the same point. We'll go with this 1.2 divided by this kind of bounces back. I think it's 310. It seems right. I mean, if it's 1.21, it's close. Okay, so we're looking around for this 387, 390 as our maximum value. So let's go with 1.20 over 3.1 divided by the square root of 2. So our maximum, or our cutoff frequency, or half power point, will be at 0.127. So looking at the data, that's going to be very close to 90,000, between 90,000 and 80,000 for the low one. So let's go not very far, just like, let's go actually like 89. I think it's very close. I think it should be very close to this. So, oops. Sure. Yeah. Increase that some. Whoops. Decrease this some. And let's see. We'll increase this. Okay. So, what do we have here? So again, the gain value that we're looking for is 0.274. And the gain value right here is between 806 and 796, so that would be what, 802 is in between, so 0.802. Yeah, or I guess 801 technically. And our other one is 289, 290, so let's see. So, close. Let's decrease it slightly. go to 87. Between 248 and 258, so what would that be? 253, or I'm saying 753. Sorry, so point. And then also our output is 2.89. All right, so that's 2.26. So let's try this 88. 0.2, keep saying 0.2, 0.777 divided by 2.89. Okay. Well, I mean, I guess if it's bouncing back between 0.777 and 0.882, that would be closer to like 780. So what if we looked at that? 0.269, 0.27, that's really close. But I'm already back up to 89, so I guess let's go to 88.5 and see if we can get any kind of close definition. So 0.78. Ugh. Okay. Between 782 and yeah, we'll go with that 787.4 over what? 2.89? Yeah. Okay. That's close. I'll call it that. So I got a value of 0.272. So I guess that would make our low cutoff frequency 88.5 kilohertz. Pretty good. Very much closer to our resonance point than previously. So again, looking at the data, our high cutoff would be what? Between 115,000 and 130. It's actually really close to 130. Just looking at the data. So I think, let me just try like, well, this is like 1.5 below the 90, so I don't know, let's try it. Let's go to like 1 below 130. See what happens. So let's go 129. So this is 0.7824 over 2.87. That's really close. It's pretty nice. So that's 0.72726, which is, I don't know, close to our target value of 0.274. So we'll call that one good. So our two values were 88.5 kilohertz and 129 kilohertz. That one came really fast. Okay, that's it. We can find our bandwidth for this 100 ohm resistor. Before even doing the calculations, you can see that it is much more narrower than the 10 ohm resistor. So that should correspond to a much higher quality factor. So yes. Okay, that concludes the data collection for this lab. I hopefully see you all next week. Well, hopefully, I guess I won't see you next week. Stay tuned for our next week's video, I guess. All right, bye.